Good afternoon, everyone. My name is Hussam Samkari. I work as an assistant professor at the University of Tabuk. I used to be a PhD student at University of Idaho. This is where all started. We got license from EMTP to support this research. And I started from that time, like about maybe 5 or 7 years ago, and we progress. And now in this point, I recently also presented a paper in the general meeting about the part of this work also. So the work is about time domain protection scheme for microgrids with IBRs and like a big scale. So I'll be going through this outline. Okay. So I think most of you guys are power engineers and maybe assuming the audience. So I just will go quickly about microgrids. So it has 2 modes, and you can either connect or disconnect it. And also we might have IBRs and storage system. And the aim is to operate it autonomously in the future, and then which will increase the resilience of the power. I'm talking about residential microgrids because the industrial type microgrids is already there. So in terms of protection, we have I divided the challenge. I divided the challenge into 2 areas. So first, we have a challenge of the microgrid itself, because we have wide variation of fault current because of the 2 modes. Also, we have maybe changing topology inside the microgrid, and we have bidirectional power. So in terms of protection, that might cause some issue, especially if we are using conventional protection schemes that is common to use in distribution system. And then if we also integrating IBRs in microgrid, which is the idea to have clean energy near residential areas, now we will have also unique fault characteristic from the IBR. We have this issue of fast response from the controllers, and also we don't have inherent inertia. So this is why the industrial microgrids started earlier. They have their own generation, conventional ones. Its system is weak, but they can play with it. But for the residential microgrids, now we want IBRs. Now it make it more complicated. So putting that in mind, we set up 4 objectives for our research to solve this issue. First, we want the protection scheme to be reliable in microgrid with inverter-based resources. So this one. Second one, it works in grid interconnected and grid isolated mode, like plug and play. We don't want to change the settings, because the relay will take some time to actually reset the settings, because I hear that suggestion. And also we want it to work on a dynamic topology. Let's say we connected in loop form, we disconnect one branch inside the microgrid. So we want that to work also. The last thing is we wanted a fast tripping scheme. And the reason is, as I said, we care about the stability, and we don't have inherent inertia. Even if you have virtual inertia, but the system is weak, not as stiff as the bulk power system. I'm just simplifying the issue here. So, for example, if we have the microgrid connected to the bulk power system, and we have the DER generating power, now the fault level is in a certain way. And then if we disconnected that, now we lose the fault current from the bulk power system. So the level is different, and the characteristic may be different because the DER is different. And in last case, if we are not generating in case of PV system, So the fault level also is different in the last case. So here's a comparison between IBR, wind type 1, and just a regular synchronous generator. We can see the IBR has very different characteristic when we compare it to generation, synchronous generators. It's about 1.2 per unit, depending on the inverter design. Could be higher if they designed it higher. Also, we have nonlinear, usually high frequency in the first quarter of a cycle. But again, this one could change if the controller is different. Primarily dependent on IBR control. This is fixed. Always dependent on the IBR controller, not dependent on the fault location, which is way different than regular conventional source. Mostly positive sequence. Okay, so when we saw all these issues, we tried to survey what we have actually on in the field of protection. We saw a high potential solution, which is superimposed, sometimes called incremental quantities, because it's fault generated component, fast. They don't change. Like if there is no zero, if there is no change, it will become zero. But if there is any change in the system, now you generate these superimposed quantities. Also, it has the capability of indicating the fault direction, which is important. So how it works is you subtract sample by sample using a buffer, like one power cycle, and then by doing that, you are calculating the delta of the change, right? And to decide which is the direction of the fault. If it's in the negative side, that means forward. If it's the positive side, that means reverse. And this is well established, and there are some papers on it, and even some real commercially available relays use this scheme. And also, commercial relays tend to have replica impedance filter specifically for the current, just to eliminate the DC offset. And then after that, they calculate the transient power, or the superimposed power. So we tested that also. We tested both. So what we found is if it's a synchronous generator, that works fine as advertised. We have the voltage, we have the current, and also the apparent power and replica apparent power, both of them are in the negative side, which will indicate the correct direction. In the wind type 1, also the same thing. But when we started to test the IBR, now we saw the high frequency missing these quantities. So you can see the high frequency in the current here, but in the voltage didn't actually play a big role here. And when we calculate the apparent power and replica apparent power for the superimposed quantities, we cannot actually decide is it forward or reverse. So this case, we have the IBR is the only source of fault current. If you are mixing and the IBR is low rating, the superimposed might work because the high frequency and the contribution from the IBR is not as strong as the generator. So what we proposed is a low bandwidth communication between relays. So we want to use the available comparison scheme. Okay, so we said let's use a comparison scheme with low bandwidth communication because we are using it in a distribution level. We want to reduce the cost. Also, we want to modify the comparison scheme to be more versatile with radial, loop, and dynamic topologies. So what we did, if the fault is in zone, we said one relay would say this is forward and the other relay says reverse. So in transmission line, we used to say both of them looking to the line, both of them should say forward. So we flipped one of the relays, And if it's out of zone, both of them forward or both of them and reverse. So this is might make it more clear. So we take the point of common coupling, even if you have different point of common coupling, but you can choose one as a reference and you go from there. Each relay send forward to the downstream, and the next relay send reverse to the upstream. And by doing that, you can actually create like a coordination and zones for the fault. If the fault happen here, the two relays communicate and trip for the fault. So let's take this example. This relay would send forward, this relay would send reverse, and it will trip. But this relay would send forward, and this relay will not send reverse, okay? So it will not trip here. So, and then we moved to the actual relay. So we proposed like a scheme that we can coordinate and apply in the radial system in microgrids. Now we move to the relay itself. As I mentioned, we have the superimposed is a good idea, but the IBR impacted that. So we tried to find a solution for it. So what we did is we have a high sampling for the time domain protection. Usually this is the case. And we calculate the superimposed quantities, but we apply a filtering scheme that make it more reliable, and we will see that in a minute. And then we have a phasor domain-based protection with low sampling, and we suggested to use overcurrent restrained with voltage. And we saw that also in research, because the dip of the voltage is high in microgrids. It's a good to control the overcurrent with it. So this is like zooming in the time domain protection. We are taking the voltage and current and calculating the superimposed quantities, and then we applied the decoupled double synchronous reference frame to clean it up. So what we are actually calculating is the positive sequence of the superimposed quantities, okay? And after that, we are taking it to find the direction. And this is the phasor-based protection, just an overcurrent controlled with voltage. Okay, so this is, I'm explaining again, this is reverse in the positive side, forward in the negative side, and we are controlling it with the change of voltage. This is the overall trip logic. We have our overcurrent, voltage restraint. Then the time domain that help us to find the direction of the fault is here. Then we have the trip logic. So this is the box that I have built the relay inside. It's huge. I couldn't capture that. So, but this is a glimpse of how I'm taking the measurements. I'm taking the voltages, the current, and then I'm taking this, the superimposed quantities, and I'm creating all that with the improved solution. So I built the relay with the proposed filter in EMTP. Also, the IBR was in EMTP, so everything was in EMTP. I didn't use another program actually to find the solution or simulate. But only the plots. Maybe I took some of the data. I used it for plots. Okay, so this is the 34 bus system that I used for testing. And this is actually, this work is published in 3 papers. One of them has this study, the 34 bus system. So I have a DER here, a synchronous generator, and I have inverter-based resources here. I was testing on 3 locations. This is a stiff part of the system. This is weak. And I tested about 120 like test using different type of faults, different type of fault resistance. Okay, here is what we improved. So you remember me talking about the superimposed apparent power. So those are the 2 that is commercially available. But when synchronous generator is there, they are fine. They indicated forward, okay? And this is what we calculated. This is the improved method. We called it watt metric. And it's in the negative side, so indicated correctly. But look here in the IBR, the apparent power from the superimposed, both of them are fluctuating between positive and negative, and you cannot tell is it forward or reverse. But our method stayed in the positive side, so we cleaned up this high frequency by applying a double rotating frame. So we extracted the negative sequence because of the IBR, and we left the positive sequence. Now we can say the energy direction, or in this case, the watt direction is in forward or in reverse. So this is a sample of the test. For example, this is grid isolated single line to ground fault location 1. And you can see this one with the conventional source, this one with the IBR. Both of them indicated the intended direction. And then we indicated the fault direction in 2.6 milliseconds, in zone in 6.6 milliseconds, and tripped 7.7 milliseconds. So this delay, because we assumed a 4 millisecond delay from communication. And this delay here, because we are using the phasor domain protection to ensure security. So when we wait for the signal to come from the other relay, we are doing our own processing for the phasor domain, and we are ensuring this is a real fault. There is a dip in the voltage, you know, so it becomes more secure, and only about 1 millisecond or so we waited also, which is pretty fast for distribution system. Okay, and here grid isolated double line to ground, the same thing, indicated correct direction. All here grid interconnected. So in the back, grid isolated, grid interconnected. The fault level changed. It doesn't matter. We still have the signal reliable. We still trip for the fault. This is some statistics, what we did, the possibilities, the fault location, the RF, and we got that from IEEE. So they have the standard of testing. So we did that. We compared the fault, the short circuit currents. We compared the power flow to validate our model. And for the calculation of superimposed quantities, I did it mathematically in MathCAD, and I verified that in a simple case. So in the average response time to trip is a half cycle, and the maximum response is about 1 cycle. So in conclusion, what we did is we tried to tackle the microgrid issue with the dynamic and with the modes. And we proposed this comparison scheme that is a little bit different than transmission line. And then we tried to find a good directional element. So we took the superimposed quantities direction element, we improved on it, we add this filter, and now it's reliable. We can use it in microgrids. So for the future, we want to like go and test more cases. Like, for example, what if we put more IBRs? What if we put change some of the synchronous generator ratings? And you know, there are endless cases and scenarios that we want to test. So basically, we want to do sensitive analysis also. One of the cases that is challenging is if you have high impedance like high RF, right? And how can you distinguish if you have a big motor between the two relays, between high impedance fault and that? So we have to do this sensitivity analysis for the protection to verify it more. And if we can get to the point of applying that for a hardware in the loop, that will be also a good thing. Thank you very much, and I'm happy to present here, and thank you for providing the license all this year that allowed us to do all this study.
Thanks to you.
Yeah, thanks.